Hello, everybody. I hope you're all doing well. Yo, Fluffs. That's what I want to say. Good to see you guys. I'm glad you guys could all make it. The show has started. I have sent the link to Professor Fulbal in Discord, so I'll just wait to see when he's going to come in. But I see he is in YouTube land. So Professor Fulbal, just click the link in Discord and you can come into StreamYard, and it'll be just us two for now. And then once you've done your presentation and everything, then I'll send the link to the people in Ellemnet to come so we can have a discussion if you want.
The hounds are chained up.
But yeah, we got Michael Kahn, Neil Constantino, PJ Cruikshank, and Disclord in the house. How you guys doing?
Yo, Flash. Jesus still loves us.
Doing well.
Absolutely good. Absolutely good.
It's good. It's good. Yeah, so guys, tonight's gonna be exciting. Eventually, the day we've all been waiting for. Professor Fulbal's coming to teach us the second law of thermodynamics. Well, I just said thermodynamics, so it can be all the laws. But yeah, it's good to have you here, Professor Fulbal. Just waiting for him still to join in StreamYard. So I'm just going to say hi to everybody in chat. So long. It's me again. Thank you for coming. Moxie7, good to see you. Sovereign Soul, hello, hello. Nathan Wright, good to see you, mate. Michael Kahn, obviously. Glenn Selch, good to see you, mate. Yannick Dazinger, great to see you. Paula, always good to see you, Bible you. Professor Fulbal, thank you for coming. Yes, I got my whiteboard here and everything ready for your presentation. Carl Oppel, thank you for coming. Glad you could make it. Dustin Bones, good to see you too. Awesome Lawson Clips, hello, hello. Brianna Johnson, hello, good to see you too. A lot of people in. Price of Adam, thank you for coming. Glad you could make it. STST, good to see you. Taylor Vision, thank you for coming. Godzilla 37, always good to see you too. FE Nation, hello, hello. And Jamie C Level, hello. Lumpy Gas in a Vacuum, it's great to see you all here. So, while we're waiting for him, what are your guys' thoughts?
My thoughts, have a good show. I'm out to take care of everybody. All the best.
I mean, I think he's just going to. I don't think he's got to listen. I just think he's got to blather on what like he usually talks. But I'm hoping it'd be nice for him to listen, and maybe I might learn something off him. But there'll be no reverting back to globe for me.
But yeah, like I said, he is willing to come teach us. Okay, he's in StreamYard. I'm gonna add him. Hey, Professor, how's it going?
How do you do?
Good, and yourself? Thank you for coming. I'm gonna. Oh, sorry. I
Sure, thank you for having me.
That's good. It's good. Okay. So, you excited? Are you feeling better? First of all.
50%.
Well, I appreciate you coming on. Let me just get my my whiteboard marker. Would you mind, before we start, maybe giving a background on who you are and your qualifications and all that?
No, I won't be doing that.
Okay.
You
but
know,
you are a professor, though.
Professor.
But you are a professor, correct?
Yes.
Did you get your qualifications in a certain field, though?
Physics, yeah.
Okay, interesting.
Yeah, particle physics to be exact.
Particle physics, okay. That's cool. Awesome. So when you're ready, like I said to the guys in Ellemnet, we're going to be just me and you here in StreamYard. And then when you're done and you want to ask questions stuff, then I'll send them the link to come in and then we'll talk like that. Is that a bit better for you?
That makes a lot of sense.
Okay.
It sounds good.
Cool.
I won't be running my camera at the same time as the lecture, but that's okay. You should be able to get my in any case, all right?
So like that, there we go.
Right. Okay. All right.
Cool.
We're good?
Yeah, all good.
All right. Okay. All right. What I'm going to need to do is to share stuff, obviously. Okay, and I did explain to you that I hadn't used this before, so...
There's a screen in the bottom that says present. You can just click that and then you can say share screen.
Sure. Share screen, yeah. So just bear with me while I just set this up, okay?
No stress.
Can they hear us?
Okay.
I can hear you, Neil.
I don't know.
Sure. Thanks. Okay. Let's share screen.
Okay, I've muted with Bill. Yeah,
Okay,
guys,
so
in
I want
Element,
to share
I
the
can hear you, so
screen.
no stress. And
Okay,
everybody on
well, I don't
YouTube
want to
can
share
hear
my
you
whole
guys.
screen. I just want to share one of the windows that I open.
Okay.
It'll give me a chance to do that.
Yeah, dude, don't worry. Take your time.
Okay, I'm not sure where that is. No. Oh, beautiful. Got it. Okay, can you see this so far?
Let me just put it on screen for you quickly. Add to stream. There we go.
Okay. I presume you can see the screen. You
Yeah.
can see that properly now?
Yeah, I can see it, yeah.
Okay. Oh, beautiful. Well. Okay. There we go. Oh, I didn't mean to do that. Okay. All right. So what we're going to be talking about is thermodynamics, not just the second law of thermodynamics. We want to make a proper lecture of this so that, maybe if you're interested enough, you'll get something out of it.
Awesome.
The audience will anyway. So what I've done is I've cut down a lecture that I previously had, put it all together so that it more or less fits the audience that we've got, and it's not too bogged down in the maths as it was previously. So it's more of a general education, if you like, on what is thermodynamics. So what is thermodynamics? Well, I think first of all we could start with why we're having this lecture at all. Okay, so, well, simply put, there are people in societies all over the world who actually think the Earth is flat and covered by a container of some sort, which, for expediency's sake, let's just call it a dome. Those people who are convinced such a thing exists don't claim to know anything about it, though. They claim not to know what it's made of. They don't know how high it is. They don't know how far it extends. And despite not having any evidence whatsoever, they claim to know with absolute certainty that it exists. So these same people who claim that space is fake, what they mean is not clear. But based on their statement, they assert that satellites orbiting Earth is not possible. They're not making this assertion because they think the flatness of the Earth or even the existence of a dome prevents objects from orbiting Earth, but rather on the notion that a place normally referred to as space does not exist. Okay. So let's see. All right, so why does it matter why flat earthers think about thermodynamics? Well, the answer's simple. Everything about flat earth hangs on a simple misunderstanding of thermodynamic principles, in particular, the second law of thermodynamics. It's the substantive reason given to support the assertion that space must be fake. Okay, the flat earth narrative goes something like this. The existence of space violates the second law of thermodynamics, and the law of thermodynamics cannot be contradicted. Therefore, space is faked. This adds the following assertions. Firstly, that gases will always fill the container they are in to create a homogeneous mixture according to Dalton's law. And this is Flatzoid's favourite law. Okay. I hope you don't mind me mentioning your name from time to time.
No stress, mate. Go ahead.
Okay.
Enjoying.
All right. So if space was real, all the gas particles on Earth would rush off and we would all die. The third assertion, satellites and other spacecraft cannot be where they say they are because the place they're in cannot exist. 4, you cannot have gas pressure next to a vacuum. 5, you must have a container to create gas pressure because gas pressure is caused by gas collisions with the walls of the container. And 6, all gases always have perfectly elastic collisions. And 7 is gases will travel indefinitely and cannot change direction unless stopped by a collision. Now, for one to assert this, something that this does not exist, it's logical that it means the object or concept could be clearly defined. You have to forgive me if my voice sounds a bit strange and shaky because I still have that illness and I'm struggling to breathe. Okay.
Yeah, don't worry. I've been struggling. I've actually laryngitis for the last 3 days as well, so my voice hasn't been up to par.
So forgive me if it's a bit shaky, but I'll do my best. Okay. All right. Okay. All right. So for billions of people, not part of the set of people who think that the Earth is flat and space is fake, space is generally described as the area above the ground where the air is too thin to support flight. So when I say too thin, I mean there are not enough particles of air to provide the conditions for the Bernoulli principle to function with enough lift, drag, and thrust to support flight. So the Merriam-Webster dictionary at point 5 describes space as the region above the Earth's atmosphere or beyond the solar system. So both are described in Merriam-Webster like that. The definition tells us little about the properties of space, however. So please forgive me for labouring this point, but in physics, words and their definitions matter. Okay, it's imperative that as much as we're able to, we need to get on the same page, especially in this conversation about the shape of Earth. All right, so let's examine the definition from space.com. Space is an almost perfect vacuum, nearly void of matter, with extremely low pressure in space. It doesn't carry because there aren't molecules close enough together to transmit sound, so we can't hear sound in space. Okay? It's not quite empty. Bits of gas, dust, and other matter floats around emptier areas of the universe, while more crowded regions can host planets, stars, and galaxies. That's a sort of a rough enough definition for it. Now, so let's concentrate on the parts of this definition we can agree with. By we, I mean the set of people who think Earth is flat compared to practically everyone else. Now, space is an almost perfect vacuum, nearly void of matter, with extremely low pressure. Sound doesn't carry because there are not enough molecules close enough together to transmit sound between them. It's not quite empty, containing bits of gas, dust, and other matter, as we read before. And above the Earth, we define space as being around 100 kilometers, which is about where the pressure is extremely low, measured to be about 0.0000146 pounds per square inch, which is about 0.10067 Pascal. Indeed, this is so low that we would not have the tools to replicate it on Earth, because we have no way of removing all the gas particles, nor can we create seals that can prevent small atoms like hydrogen from overcoming the seals. So in other words, if you're going to make seals out of rubber, you're going to have a hard time stopping the smallest atom like hydrogen. So space below 100 kilometers accounts for around 99.997% of Earth's atmosphere, and the area between the ground and 30 kilometers accounts for around 99% of Earth's atmosphere. But this does not happen suddenly. The drop in pressure is exponentially less and less. Let's have a look at this graph, and you can see from here, you can see that it's an exponential graph. So the pressure starts quite high at the bottom and rises rapidly, exponentially higher and higher, and gets much, much less and less. So in a very short space of time, it's quite small. Now, is there any evidence that most of the atmosphere is below 38 kilometers? Well, there certainly is, both visually and measured. Is there evidence that an area above the Earth meets the definition of space? Well, indeed there is. Okay, there it is. You can see it right there, right here in this very photo, and many photos like this. So flat earthers, like Flatzoid and others, do agree on some basic undeniable facts, such as high altitude balloons that can reach approximately 40 kilometers, encompassing most of the 99% of the Earth's atmosphere. Flat earthers and other private operators have even launched their own high altitude balloons with cameras. This view is always the same in daylight: a thin blue area that hugs the ground, followed by a black area. It's vast. It gets exponentially deeper black with altitude. As you can see from these photographs, now on numerous occasions, right from my first foray into space, on hearing the assertion that space is fake because it violates the second law of thermodynamics. No, I'm not saying that I've been to space. I'm just saying this space, as in, flat Earth. Okay. I've asked obvious questions. For instance, what is preventing the air at the ground, where the pressure is on average 14.7 pounds per square inch, from rushing to fill the black area of the sky that goes beyond the blue area? Okay. All right, so is there evidence that an area above the Earth that meets the definition of space? Indeed there is. So this is it. So you can see from this photograph where I've added some arrows to it, we've got 100 kilometers sitting above the Earth with 0.0000146 psi, and then at the ground starting at 14.7, that thin blue area going to about 30 kilometers. All right, so the particles go all the way to the dome. Not a second. So, well, what are we saying that flat earthers say? They say that the particles go all the way to the dome and back again to settle in the blue area under 30 kilometers. Now, forgive me if I'm straw manning you, but that's what I understood that you said that yourself. I could be wrong. Now, the area is always black, suggesting that air particles take turns. Perhaps it's their impulse. Volume of space beneath the dome changes with altitude. This is another one of the rhetoric. And apparently when you're on the ground, there is less volume around than if you're on the top of a mountain. But the most important one from you, my friend, is that you say it's gas behavior, which is okay. And so you'll throw that word around quite a lot, but you never seem to tell us what gas behavior that you're talking about. But we'll come to that. Right, so let's have a look at this animation. can see that we've got a box here. Yes, it is a container. And you can see how the gas is moving in. Some of the gas particles will hit against each other and others will hit against the wall of the container. So that's pretty straightforward. Okay, so let's put some objects in that represent, hills and mountains and the like. So my friend, you think that there is less volume in this container at the bottom than at the top. And you think there is more pressure at the bottom because there's more stuff for the air to bounce off. Okay, so I can assure you in this container the pressure will be the same everywhere. Never mind, let's carry on. All right, let's have a look at some more of this flat earth rhetoric. Okay, so one of the laws of physics that flat earthers refer to as the law of nature is in fact the second law of thermodynamics. Now let's have a look at some of that, the facts on that. Well, first of all, two irrefutable, unwavering, unchanging, unforgiving properties of the second law of thermodynamics follows. First of all, it's irreversible. And secondly, entropy only happens in one direction. For reasons you think will assert that you assert why the air at the ground does not rush to fill the vast black area, the fact remains that it does not do that. So you have your reasons for why it doesn't do it. You call it gas behavior, that's fine. It doesn't do it. And given the near vacuum conditions in the black area, which we've established, like assertions about space, must, according to flat earth catechism, be violating the second law of thermodynamics. So clearly there's a black area, clearly it's got very, very low pressure, clearly the gas in the thin blue area is not rushing to fill that black area. So if you think thermodynamics has anything to do with that, it's obviously violating the second law of thermodynamics. It's not happening. There must be some other reason. We'll explore that. Okay. All right. So let's not forget the flat earth narrative that according to flat earthers, if space was real, the second law of thermodynamics would ensure that all the air at the surface would rush to fill the area we call space. So clearly in the flat earth universe, the second law of thermodynamics must be asleep. So alternatively, Flatzoid, his crew, plus the flat earth bosses and their minions are wrong about what the second law of thermodynamics applies to. It seems to be completely lost on all the flat earthers that the second law of thermodynamics is not working as they think it should. Well, there's more about that later after the main lecture on thermodynamics. Now, all right, so let's have a look at it. That's what we're talking about. Well, first of all, having participated in this flat earth, globe earth arena for several years, I'm not deluded enough to think that rusted on flat earthers will change their minds about the shape of Earth by actually absorbing the evidence and the underpinning physics. Flat Earth is not a conclusion one draws from evidence, simply a posture based purely on faith and interpretation of specific scripture, together with a propensity to buck the system and engage in conspiracy theories. The flat earth conspiracy theory being arguably the most outrageous. Lots and lots of people have been lying to you for many, many centuries. That's primarily because it asserts dishonesty and untrustworthiness of millions and millions of ordinary good people who were sufficiently intelligent to pursue careers in physics, chemistry, mathematics, engineering, and so on, which underpins the myriads of disciplines that encompass the human experience as far back as 2,500 years ago. So this lecture is to teach the basics of the first three laws of thermodynamics, and that's sufficient enough to dispel the innate understanding about thermodynamics and therefore dismantle the reason why flat earthers use to assert that space is fake, and also to dismiss out of hand all the evidence that involves space. Okay, so basically we're going to try and establish that those reasons why you think space is fake are not true. Okay? So this is not a comprehensive lecture on thermodynamics. Okay? It's a highly cut down and simplified version to suit the YouTube audience. So just looking at thermodynamics, as you can see on the screen here, first of all, what is heat? Okay, so heat is the transfer of energy from one body to another due to a temperature difference. Kinetic energy, EK is half mv squared, is the energy associated with the movement of objects, like all forms of energy. Gravitational potential energy, that's the energy stored in an object as a result of its position relative to another object to which it's attracted by the force of gravity. A joule, that's the SI unit of work or energy. 1 joule is the energy expended when the force of 1 Newton acts through a distance of 1 meter. Between heat, work, and internal energy of a system and its interaction with its environment. So, to get an appreciation of how heat works, it's necessary for one to examine the laws of thermodynamics, and particularly the zeroth law, the first law, and the second law. There's another one, but that's of no consequence for this discussion, so we'll just have a look at these three laws. Okay. Now, first of all, thermodynamics, as the name suggests, is the study of the dynamics of energy, particularly heat energy. Thermodynamics is not concerned with the matter itself, except for describing how the dynamics of heat energy affects that matter. The actual subject being described by thermodynamics is heat. Right. For example, thermodynamics is not concerned with how a gas under pressure escapes to an area of low pressure, but rather the dynamics of thermal energy that's involved in the event. Thermodynamics is the consequence of the gas escaping from a high pressure to a low pressure, not the reason for it doing so. So we'll talk about that in detail later when we get to discuss Earth's atmosphere, and in fact the atmosphere around other planets, which of course is indisputable. They're empirical fact, we measure them. All right, so let's start with the zeroth law of thermodynamics. Okay. Well, first of all, before that, Earth has an atmosphere which is obvious. We can use it. Other planets also have atmosphere which we can measure, which, whether or not you refer to those planets as wandering stars, twinkling fairies, or Flatzoids, foibles, the simple, indisputable fact is that humans have observed, measured, and analyzed the atmosphere of those bodies.
I'm gonna burst.
Okay, so
he likes to insult us, doesn't he?
the zeroth law of thermodynamics states that if two bodies are each in thermal equilibrium with a third body, they are also in equilibrium with each other. So as you can see from this diagram, if A is equal to B and B is equal to C, then it follows that A must also be equal to C. It's pretty straightforward. Okay. So thermal equilibrium means that when two bodies are brought into contact with each other and separated by a barrier that is permeable to heat, there will be no transfer of heat from one to the other. They are at the same temperature. All right, so let's have a look at the application of the zeroth law of thermodynamics. Well, the zeroth law of thermodynamics defines temperature. That's pretty much where temperature comes from, and makes thermometers possible. So in the early 18th century, the German instrument maker, Daniel Gabriel Fahrenheit, invented the familiar glass tube thermometers using both alcohol and mercury. A thermometer works by the transfer of heat from the hot body to the liquid inside the capillary of the thermometer, causing it to expand until it reaches equilibrium with the hot body. That's why you've got to wait a little bit for the temperature to reach equilibrium before you read the temperature on the temperature gauge. So you need to wait for that time for that equilibrium to happen, so that the temperature inside the thermometer is equal to the temperature outside the thermometer. Well, to the stuff that you're measuring. Okay, unfortunately, I thought I'd just throw a bit of fun in here. The poor Americans, they stuck with this Fahrenheit system. Okay. All right, let's carry on. Okay. All right, so in the Celsius scale, Anders Celsius in 1742, he decided that the freezing and boiling point of water would be separated by much more sensible 100 degrees. So in the Fahrenheit system, it was separated by 180 degrees. In this system, in the Celsius system, it's 100 degrees, much easier to work with. And he made the freezing point of water at 0. This is an arbitrary thing, and the boiling point at 100. So just deciding what they were. It just isn't something that came from magic. It was it's an arbitrary number on the scale. And because Celsius is pretty much 0 to 100, that made dealing with temperature much easier. And then along came the Scottish-Irish physicist William Thomson, and who was later called Lord Kelvin. Well, he fixed the problem of negative temperatures. So the problem with the Celsius scale was that 0 degrees wasn't as cold as you could get. You could get much colder than that. So therefore, anything colder than 0 Celsius meant you had to go into negative figures, and that caused all sorts of problems with calculations. So this physicist, William Thomson, came along. Lord Kelvin, he, by the way, responsible for formulating those laws of thermodynamics. He came along and coined the Kelvin scale, which is in his name. So he was one of the most eminent scientists of his time, and best known for inventing the international system of absolute temperature that bears his name. All right, one of the giants of science that that all of us rely on. Okay, let's proceed. All right, so let's do some practice. I know you've all been waiting for this. So here's the first question. If a gas is in a closed container and pressurized from 15 atmospheres to 25 atmospheres, and its original temperature was minus 20 degrees C, what would the final temperature of the gas be in Celsius? Well, which gas law does this question relate to? Well, that's an interesting one. And predict what temperature this will be. Well, let's have a look. Hopefully I actually did this correctly. Well, first of all, it refers to the Gay-Lussac law. The pressure of a gas is directly proportional to its temperature, while the volume is kept constant. Of course, this could not apply to the atmosphere, because it also assumes that the temperature and pressure is constant in the entire container. We know that's not the case. We had a look at it before, and if there was a container above the Earth, it's certainly not the same everywhere. There's all this area above, it's black, it's very, very low pressure. Then there's that blue area that's got relatively high pressure. It's not constant, so Gay-Lussac's law would not work in that particular thing. We couldn't use it. In fact, we couldn't use any of them. So Gay-Lussac's law basically talks about the pressure P1 over T1 is equal to P2 over T2. So pressure is proportional, directly proportional to temperature, and the pressure divided by the temperature gives us a constant. Okay. Okay. All right. So predict what the temperature will be. Well, P1 over T1 equals P2 over T2. So we can switch that around so that P1 times T2 is P2 times T1. And if we switch that so we can get T2 as our subject, T2 is equal to P2 times T1 divided by P1. So firstly, convert the temperatures to Kelvin if there are any negative ones, which there are. So minus 18 degrees is 273 minus 18, which is 255 Kelvin. And then substitute the data into the equation. T2 is equal to 25 times 255 divided by 15 gives us 425 K. Okay, so well done those of you who gave it a go. Remember, these simple laws cannot work for the atmosphere because the atmosphere is a gradient. Okay. All right, so to model the atmosphere, we'd need a great deal of calculus to do that, because it's not linear. Okay. All right, let's go around. Okay, so flat earthers influences. I presume you're one of those, my friend. When the atmosphere is mentioned, please refrain from blurting out gas laws or any of the main models like Boyle, Charles, Gay-Lussac, the combined law, the ideal law, Dalton's law exactly. The pressure gradient makes them oversimplified. You may be able to trick your friends, but people who actually know this stuff will just think you're being silly. You can't use these laws in the atmosphere. Okay? They just don't apply the way they in the simple way that you would use them in a container. All right, so let's have a look at the first law of thermodynamics. All right, so conservation of energy is exactly like the conservation of mass, meaning it can be neither created or destroyed, but it can be transformed from one form of energy to another. Okay, so whenever a system experiences any change due to the interaction of heat, work, and internal energy, we observe numerous energy changes and conversions. However, during these transfers, there's no net change in the total energy. We're not going to create energy out of the blue. I'll get to that Big Bang thing about that shortly, okay? Because I know that must have popped right into your head. The first law of thermodynamics affirms that heat is indeed a form of energy. What it means is that the thermodynamic processes are governed by the principle of the conservation of energy. That's why the first law of thermodynamics is also sometimes referred to as the law of conservation of energy. All right, so let's state the law of the first law of thermodynamics. The first law of thermodynamics explicitly states that the energy of the universe remains the same, although it may be exchanged between the systems and the surroundings. It can't be created or destroyed. The Big Bang does not violate the first law of thermodynamics because the proposed singularity already contained all the energy that the universe will ever possess. So we're not making anything new. No one's proposing that there was nothing there. We're saying that there was some singularity, and it already contained all of the energy that was ever going to be available in the universe. So let's have a look at this, some equations. Let's have a look at the equation for the first law and a demonstration of this in reality. First of all, that the change in internal energy is equal to the energy plus work. So internal energy is equal to the energy at the end minus the energy at the beginning. All right, so EI is internal energy, initial energy, and EF is the final energy. Okay. So let's have a look at the equation for the first law and a demonstration of it in reality again. So that's the equations on the left-hand side, and we can see more clearly what we mean by those variables. So Q, that's the heat flow into the system. So if the heat flow into the system, that's the meaning of the plus sign, and the meaning of the minus sign, heat flows out of the system. So whether you have minus Q or plus Q depends on those two things. W is the work done on the system, and for the meaning of the plus sign for W means that surroundings do positive work on the system, and for W, in a negative W, surroundings do negative work on the system. The system does positive work on the surroundings, in other words. Okay? And then, of course, delta U means the internal energy change. If the delta U is plus, then the internal energy of the system increases, and if the delta U is negative, then the internal change decreases. Okay, so this is an example of the first law of thermodynamics, the conversion of food into energy that is used by the body to perform activities. The metabolism in humans is the conversion of food into energy, which is then used by the body to perform activities. It's an example of the first law of thermodynamics in action. I'm going to press on. Hopefully you can see that diagram. You can understand that this is about food and energy, the conversion of food into energy, which of course you need.
Transformation.
Okay, and just to understand what ATP is the energy needed to perform cell functions such as DNA replication, mitosis, meiosis, cell movement, you name it. Okay. All right. Right, so example of the first law of thermodynamics, as you can see, the sun contains UV radiation, which is absorbed by the plants and trees, and plants absorb this solar radiation and store it in the form of chemical energy. So that's how plants end up using the sun, using photosynthesis. They've got particularly cells that are able to convert the energy from the sun into and combine that with other nutrients and produce the actual matter of the plant. Okay. All right. All right, so let's have a look. How do we know if we should make Q and W negative or positive? Well, first of all, if a system absorbs heat, then energy from the for example, we're getting it from energy from the sunlight, then Q is going to be greater than 0. If the system releases heat, Okay, so releasing meaning it's exothermic. For instance, when you sweat, you're releasing heat, then your energy will be less than zero. Okay. Then if the system does work on the surroundings, okay, for instance, a hot balloon expands, then work is going to be greater than zero. And if the surroundings do work on the system, in other words, if you're pumping up a tire, then work is going to be less than zero. So this leads us into another question. All right, so first of all, A, let's have a look at this question. Really nice question. Okay, a balloon is placed in direct sunlight. The sunlight supplies 200 joules of energy into the balloon. The air inside pushes out the balloon's surface, doing 50 joules of work. Okay, by how much does the internal energy of the air inside change? And B, part of that question is, a large block of ice heated by 100 joules of energy does not melt. What is the change in the internal energy? So I want you to have a look at that, and you know that I'm not very well, so I'm just going to go and have a quick glass of water while you get your pens and papers out and calculators and see if you can work this problem out. I'll be back in 1 month. Okay, Keith?
Just want to quickly, while he's gone, guys, just say thank you for the super chats. Let's quickly go read them out. Sorry I haven't read them out, but we are letting him give his free time. Thank you, Godzilla37, for your $5 super chat. No human should have to listen to Phil this long. Patience is of a saint. Thank you very much, Godzilla37, for your super chat. Tony Whitcomb, £20 super chat. We've now found the last Monty Python character on a live show. Thank you very much for the super chats, guys. You guys are very much appreciated. Really appreciate all the support. You guys rock.
I just want to know, Flats, me as a minion, what's the next thing you want me to do, sir?
well remember, we got bosses, and apparently Michael's my boss, so, and Michael, I still haven't got any pay.
I was going to say, I'm not a minion, I'm Gaffer.
Yeah,
I think you're Gaffer, dude.
I still haven't got any pay from you. What's going on, man?
Isn't it, dude? I'm quitting.
You read it Never Never, aren't you?
Nice.
Okay, so balloon is placed in direct sunlight. The sunlight applies 200 joules of energy to the balloon. Note the balloon has containment, guys. The air inside pushes out the balloon surface, doing 50 joules of work. By how much does the internal energy of the air inside change? By 50 joules. So it's 150 joules then.
All right, let's have a look and see
minus.
that. And yeah, very good.
Yeah.
Okay, let's have a look at the solutions. So first of all, for A, well done, my friend, you're pretty good. Okay, so recall the relationship just to help others. Okay, if we recall the relationship is the change in the system is the energy minus the work. So if we identify the variables, so whenever you're doing physics problems, it's best to write down what your variables are. You could work on them. So Q is 200 joules and work is 50. So we substitute that in the equation, 200 minus 50, 150 joules, as Flatzoid pointed out. Very well done. Okay. For B, I didn't give you a chance to do it, but never mind, we'll do it together. Again, recall the relationship. Q minus W. This time, identify the variables. System is the ice block. Heat is added to the system, so Q is positive. Remember, we had to look at the table about when it should be positive, when it should be negative. Okay, so no work is done because the ice doesn't melt. So Q is equal to 100. Work is 0. So therefore, the change is no change. 100 joules. We state the solution. The internal energy of the ice has increased by 100 joules. Okay. Okay, here we go. Here's our friend right there. All right. Okay, the weightlifter. All right. So while doing some heavy lifting to impress his panel friends, Flatzoid does 2,500 joules of work on the weights while releasing 3,000 joules of heat. By how much did his internal energy change? We'll just jump straight into it for expediency's sake. Okay. So there you go, Flatzoid. I can see you struggling with those weights. I hope you didn't mind me using
No
that.
stress, man. It's funny.
All right, so the answer: heat is removed from the system this time, so Q is negative. All right, so number 2, collect your variables. Q is minus 3,000 joules. Like I said, it's removed from the system, and W is 2,500. So minus 3,000 minus 2,500 gives us minus 5,500 joules. So if we state a solution, his internal energy has decreased by 5,500 joules. By now, our friend Flatzoid would be feeling fairly tired because he's given away this energy. Okay, let's have a look at the second law of thermodynamics this time. Okay, and that is... Okay, so the second law of thermodynamics states that the state of entropy of the entire universe as an isolated system will always increase over time. The second law of thermodynamics, by the way, the universe is the isolated system. When we talk about an isolated system, we talk about the universe. The second law of thermodynamics, it's the Clausius statement. Heat never flows spontaneously from a colder body to a hotter body. Okay? Any process that involves dissipation of energy is not reversible. This does not apply to gases dispersing, which is reversible. Okay. Any process that involves heat transfer from a hotter object to a colder object is not reversible. This does not apply. Oh, I said that before. Repeating myself. Okay. So, how is the dispersion of gas particles relevant to the entropy of to the entropy of energy? It doesn't. It's irrelevant. Why? Because the dispersion of gas particles in a container is a reversible process, and therefore is contrary to the entropy of energy, which is irreversible. Okay, so there are some demonstrations of analogs of the second law of thermodynamics that seems to be popular. Okay, seems to be popular with some flat earthers. Is this thing on the screen here that's making me trying to hide? Let's try hiding. There we go. Okay, that seems to be popular with some flat earthers who are hell-bent on tricking their followers into believing space is fake because of the second law of thermodynamics. Okay, here's one example. Let's have a look at this one closely. So here is one where the instructor heats up some bromine in a flask, which is sealed to another flask while a stopcock is in between. You can see from that diagram. We know the instructor has applied heat to the flask containing the bromine. That's because bromine is in the gas phase in this demonstration. At normal temperature and pressure, bromine and mercury are the only two elements that are liquid at normal temperature and pressure. Okay, so bromine's a liquid. So obviously, at room temperature, that flask on the right would have been filled with a liquid. Well, not filled, but they would have added a liquid bromine to that flask, and then this instructor would have heated that up, so added energy to the system. Okay, that's yelling at me. Just 1 second, please.
No stress.
Okay, so The instructor also uses a vacuum pump to evacuate the air from the other flask to create a vacuum. So now we've got one flask on the right hand side, and that's got a certain amount of bromine that's being heated up. If you heat it up, of course, it turns from a liquid to a gas, and there's a stopcock in between, and then on the other side we've got created a vacuum. It doesn't have to be much of a vacuum, but just enough. So you can see from that diagram we've got bromine gas and a vacuum on the other side. Okay. All right. So then the opens the stopcock between the two flasks, allowing the bromine to expand into the vacuum flask. The dispersion of the bromine is analogous to the entropy of energy, but only insofar as the bromine expands to fill the vacuum. Beyond that is not an analog for entropy. That's because the process is reversible. That's the point, which is a fundamental violation of the second law of thermodynamics. It should not be reversible. That's why the actual gas itself doesn't rise to the level of the second law of thermodynamics. It's the energy that does. Okay, so where is the actual thermodynamics process taking place? Well, it's the hot gas particles colliding with the walls of the flask, and on every collision loses a small amount of heat energy, which is absorbed by the glass. The energy travels through the glass and is radiated away or passed on to air particles outside of the glass, dissipating into smaller and smaller fractions. Collecting this energy in order for it to make it do work is impossible. This is the quintessential process of entropy and the very definition of the second law of thermodynamics. So if you can see over here in this diagram, you can see that the energy is radiated out from the glass. So that's where that's the entropy that's taking place. Okay, delta S is equal to delta Q over delta T, which is the formula for entropy and the very definition of the second law of thermodynamics. The important point that I'm trying to make here is that the energy leaving the system here is irreversible. But the gas that's in there, we can turn that back to a liquid. All we need to do is to wait long enough for that extra energy that was put into the system to leave, and the gas will condense back into a liquid, okay, making it a reversible process. So 100% of the bromine condenses back to liquid phase. It's not lost in entropy. It's not the one direction. It's not irreversible. It's reversible. Only the heat energy experienced entropy here. So again, as I said before, delta S is equal to delta Q over delta T. All right, so the net result is that the bromine will eventually reach thermal equilibrium with the surrounding air and condense back into liquid bromine. The equation for entropy, as I said before, delta S over delta T. Okay, in other words, the change in entropy increases in the change of entropy increase is equal to the change in energy in joules over the change in temperature in Kelvin. Flat earthers who use this demonstration to trick their followers know this and are being less than intellectually honest. So we know it's not the gas itself, it's the energy, it's the heat that's doing the entropy. Okay, a similar analog to entropy is run by an MIT professor who draws two boxes on the chalkboard and explains how the gas in one would dissipate into the other while conserving energy. Of course, in reality, whatever material those boxes are made from, they're not immune from absorbing heat, which is transferred to the walls during collisions. The gas, what happens to the gas is a consequence of the heat. Okay, it's not the reason, it's not the entropy that's taking place. The heat the heat dissipation, the heat being lost, not being able to use that to do work. That's the entropy. So let's consolidate what we've learned by doing an example calculation. And Flatzoid's pretty good at this, so maybe he'll have a crack at this one too. Okay, there you go. So let's consider the following problem. A reversible heat engine receives 3,000 kilojoules of heat from a constant temperature source at 380 degrees C. Okay, if the surroundings is at 25 degrees C, let's first of all determine the availability of the heat energy, and then we can have a look at the unavailable heat. All right, I'll just move on because it's
time.
Time. Okay. All right. Okay, so let's have a look. First of all, when you're doing a problem like this, then like I said before, in physics, you write down your stuff. Write down your variables first. So Q1 is 3,000 kilojoules, T1 is 380 C, and T0 is 25 degrees C. So with dealing with the available energy, first of all, you need to change all those temperatures into Kelvin. Okay, as I mentioned before. All right, so T1 is going to be 380 plus 273 degrees, so 653 degrees Kelvin. T0 is 25 degrees C plus 273, which is 298 Kelvin. Okay, if you apply the formula, delta S equals dq over dt, you'll find, substitute into that formula, and you'll find that delta S is 3,000 divided by 653 plus 298 gives us 3.15 Kelvin, kilojoules per Kelvin. So that's the units for entropy, okay? Kilojoules per Kelvin. All right, so 2,061.3 kilojoules. That's the available energy. So let's have a look at the unavailable energy. The unavailable energy, that's pretty straightforward, is going to be equal to T0, so which is going to be 298 Kelvin times the 3.15 kilojoules per Kelvin. Yep, and we end up with 938. I would have let you do that, Flatzoid. I know you would, but it's just a bit of time. Okay.
No stress.
All right. So had we had more time, I'd say good job, everybody, for doing that. Let's continue. Okay. All right. So let's have a look at heat transfer in thermodynamics and the kinetic theory of matter. This is really important to the question that we're talking about. Okay. So here's some definitions to add to your notes. All right. So this is important. This very, very first one. Okay. So I want you to pay attention to this one, Keith. Translational kinetic energy. That's the energy due to the motion of an object from one location to another. Okay, I know you like to describe the energy as the wiggling and the jiggling and all that, which you're wrong. But it does more than that. It has translational kinetic energy. In other words, it moves long distances. Okay, the vibrational kinetic energy, which is what you're talking about, is the energy due to the vibration motion of objects. Rotational kinetic energy is the energy to the rotational motion of objects, as you can see from this diagram. Okay, so have a look at this over here. This is a CO2 molecule that's going through translational energy. It's moving up and down. Vibrational energy, wiggling, and then we've got the rotational energy where the molecule can actually rotate. Those are the three different lots of movement. But the important one I want you to keep in mind is the translational kinetic energy. Okay. All right. So the kinetic theory of gases, which ties all kinetic motions to temperature, and particularly translational kinetic energy to atmospheric gases, is underpinned by solid empirical evidence. This isn't something we just made up. The translational kinetic energy of the ideal gas. I should point out here before I carry on with this, there's actually no such thing as an ideal gas. Okay? All right, it's a model that we use so that you can have inputs and outputs that that you can make predictions on, but there's not an actual ideal gas. All right. So if you wanted to get very, very precise, then you do some experiments to get the actual data, the empirical data. But in any case, we need to work with models like this because we can't be testing every single thing every single time. Okay? Like producing a new constant every time. So we get a constant that within a certain level of precision works for mostly all the gases. Okay. So in this case, we're saying that the energy is 3/2 kT. That's where E is the average kinetic energy of the gas, T is the temperature of the gas in Kelvin, and K is the Boltzmann constant. All right, the Boltzmann constant, that's the value of 1.381 by 10 to the minus 23 square meters per kilogram per second squared per Kelvin. In a simple terms, we can just reduce that to joules per Kelvin, which is entropy, the units for entropy. Okay? 1.381 by 10 to the minus 23 joules per Kelvin. All right, for lay people, flat earthers and normal people alike, this simply means that the hotter a particle is, the faster and further it'll travel in classic ballistic motion. And while slowing down, it loses kinetic energy and drops in temperature, while the heat radiated from those particles experience irreversible entropy. Right, so the kinetic theory of gases relative to the atmosphere predicts that gas particles will have varying initial translational kinetic energy. Not all gases are going to travel at the same speed. Not all gas particles will have the same momentum. Not all gas particles will reach the same altitude before being overcome by gravity. Let's see if we can calculate the kinetic energy relative to altitude. It's an interesting one. This happens in aeroplanes all the time. Okay. All right. Calculate the kinetic energy of one molecule of oxygen at 25 degrees Celsius and minus 50 degrees Celsius. That's the commercial cruising altitude. Right, so let's look at our formula. EK equals 3/2 kT using Boltzmann's constant for atmospheric conditions. I should point out the other constant is 8.31, which is the ideal gas constant.
Yeah, which the
so the difference between
because the Boltzmann's in the ideal. So yeah, that's how they use the 8.1.
Yeah. So there's two. So basically there's the Boltzmann constant, which deals with a molecule. Okay, there's the ideal gas constant, which deals with a bunch of molecules. Okay, so that's the difference between them. So EK is 3/2 kT, using Boltzmann's constant in this case because we asked the question one molecule of oxygen. So convert again 25 degrees C to Kelvin, we get 298. When you work with this a lot, then you know that you practically know that one by heart. Boltzmann's constant 1.381 by 10 to the minus 23 joules per Kelvin. Substitute that data in. 25 degrees is at C. We get 6.16 by 10 to the minus 21 joules. At minus 50, we get 4.616 by 10 to the minus 21 joules. You can see that higher you go, the less energy there is. Okay. All right. Okay, so clearly the higher you go, the less energy air particles have. So because particles of air have different translational kinetic energy, remember that word, okay, their weight will be equal to the kinetic energy, which means they'll have a very limited amount of translational kinetic energy, allowing them to oscillate between the narrow bands of altitude. Okay. By the way, flat earthers can describe the downward acceleration however they want. Okay. The magnitude of the acceleration is what matters, not what you call it. This accounts, Keith likes to call it unicorn farts or whatever. That's fine. call it whatever you like, okay? But the fact is, there is a downward acceleration. Those gas particles will eventually get as far as they can with energy, and eventually that downward acceleration, whatever you want to call it, unicorn farts is fine with me, will overcome that, and they'll not be able to get any higher. So this accounts for the fact that 99% of the atmosphere does not have sufficient kinetic energy to overcome their weight. Okay? It accounts for why the air particles in the blue area of the atmosphere from the ground to 30 kilometers does not rush to the near vacuum at 100 kilometers and beyond. It also exposes the straw man used by flat earthers to deflect from the reality by suggesting that space must be fake because of the second law of thermodynamics. All right, so let's finish up with the two heat transfer processes relevant to this atmosphere. That's conduction and radiation. So we'll talk about those two things. So here we've got Q equals minus K delta T. Right? So Q is the local heat flux density. Minus K is the material's conductivity. So that's an empirical thing when we talk about the material conductivity of things. You need to measure it, and then create tables and books with all sorts of materials, and each one of those has a measured amount of that conductivity. So that's empirical. Then there's the change in temperature gradient. All right, so you can see from that diagram how that happens with conduction. Conduction is the transfer of heat through a substance that's a result of collisions between neighboring vibrating particles. The particles in the higher temperature region have more random kinetic energy than those in the lower temperature regions. Okay. All right, so the more energetic particles collide with the less energetic particles, giving up some of their kinetic energy. This transfer of kinetic energy from particle to particle continues until thermal equilibrium is reached. There's no net movement of particles during the process of this collision, of this conduction. Solids are better conductors of heat than liquids and gases. In solids, the particles are more tightly bound and closer together than in liquids, and thus kinetic energy can be transferred more quickly, right? So, transferring is much easier if you're really, really close. Metals are the best conductors of heat because free electrons are able to transfer kinetic energy more readily to other electrons and atoms. You can see, so in metals, for instance, the electrons are on the outside of it. Let's say, for instance, we're running electricity through a piece of wire. Electricity doesn't run through the middle of the wire. Okay, electricity runs through is running on the outside of the wire. Okay, because that's where the electrons are. So that's where the electrons get to move, not through the middle of the wire. Okay, so if you've got a bigger, thicker wire, there's more surface area around it. More surface area means more electrons around it, able to. So that piece of wire that's thicker, not because it's thicker so more electricity can run through its middle, it's because it's got more surface area around it that allows more electricity to travel. And by the way, in case you didn't know this, electrons are responsible for why they're shiny. Okay, so they're shiny because of the electrons.
That I knew. That I didn't know.
Okay, all right. So just a quick diagram. You can see those two diagrams there with the direction of heat transfer. From high temperature to low temperature. Okay, so you can see how that happens. So you're holding a handle, something like a nail in your hand, and you heat it up. Eventually, it's going to burn your hand. As the temperature increases across. So that's what we're talking about when we're talking about conduction. Okay. All right. So let's move on to radiation. Radiation is quite different. You can see that diagram's got all three of them really. You got convection, which is the heat coming up from the top of from the fire, and that convection goes around and round in cycles. okay, which is mostly what we have in our system. We've got conduction, which is again holding the poker and getting hot, and then we've got radiation. So this is radiation is electromagnetic radiation. So okay, so all objects with a temperature above absolute zero emit electromagnetic radiation through the process of black body radiation. So visible light, microwaves, infrared radiation, ultraviolet radiation, and X-rays are all examples of electromagnetic radiation. They're all the same stuff. It's just that they're the same stuff at different energy levels. So let's have a look at some types of radiated heat. Okay, first of all, the transmitted radiated heat, like clear objects like glass, allow light and radiated heat to pass through them. Right, the temperature of these objects does not increase quickly. Well, they do increase somewhat, but not quickly when heat reaches them by radiation. Why they do get hot is because some of that radiation is absorbed. Okay, so when you've got things that are particular types of glass that you don't want to absorb heat, then these are very, very expensive glasses. Okay, you've got absorbed, you've got radiated heat, right? That's absorbed radiant heat. So dark colored objects will tend to absorb the light and radiant heat, and their temperature increases quickly. So, for instance, if you step outside without shoes on a dark road, you're going to get burnt. Reflected heat, radiant heat, that's shiny or light colored surfaces tend to reflect light and radiant heat away. So if you want something to, like this shiny stuff you put in your windscreen on a very hot day, reflect the heat, as much of the heat as you can away from you. Okay, so the temperature of these objects doesn't change quickly. Okay, they radiate the heat away, but they don't get hot themselves. Okay, all right. So what distinguishes the different types of electromagnetic radiation from each other? Well, first of all, their wavelength. That's the distance the wave takes to repeat itself. Okay, so it's really peak to peak. Okay, so that's the length of the wave. Right. Their frequency, that's the number of wavelengths passing every second. The amount of energy they transfer. So when you think about a wave, and we'll talk about intensity, then that's the amplitude, right? So how tall is it from the bottom of the wave to the top of the wave, right? Okay, so these properties in turn determine their ability to be transmitted through transparent or opaque objects. All right, the heating effect and the effect on living tissue, for instance. All right, so here we're having a look at the actual electromagnetic spectrum. So remember, like what I said, it's all the same stuff, different energy level. At the left-hand side, you can see this is that's AM radio. So these are photons at very, very high, right? This very, very long wavelength. See, 10 to the 4 meters, right? That's a long way. That's like 10 kilometers, right? Okay, and you can see 10 to the 2. That's 100 meters. Then you've got down to 1 meter. 0.01 and so on, so right down. So these are quite long wavelengths in this red area, and heat is sort of in that 10 to the minus 4 area. Then we've got visible light, that very, very thin band of raw GBeV, as everyone knows. That's just the visible light. So humans can only get to see in that very, very, so our eyesight can only pick up the cells in our eyesight, the rods and cones can only pick up wavelengths in that tiny, tiny band. We can't actually see any of the rest of it. But if you've got some animals around, they can see a bit more either side of that. So for instance, like the dogs, they can actually see in the dark. The cats can see in the dark. so they can see where they're going. It looks perfectly normal to them. You can't see a thing. Okay. All right. So on the right hand side, we've got very, very high energy. So ultraviolet radiation. That causes skin cancer, and that's one of the reasons that I'm having problems. And that is produces a lot of melanoma and that type of skin cancer, particularly in the south over here in Australia. It's very, very common. And then we have further that we have X-rays, very high energy photons, and then gamma rays, which are extremely dangerous to human life, to any life. In fact, if you're going to an airport and they take some stuff off you, like wood or something like that, they might tell you, listen, you can have it provided that you pay for it to be irradiated. And then they'll take it somewhere and they'll hit it with gamma rays, and if there's anything that's alive in there, it won't be alive after that. Okay. All right, so that's the electromagnetic spectrum. All right, so why do hot objects emit electromagnetic radiation? Well, this is a very, very simplified way of doing that. Technically, it's if you think about an atom, it's got electrons around a nucleus. Okay, and if it's in its normal state, the electrons are a certain distance from the nucleus at different energy levels. So some electrons are closer to the nucleus, others are a bit sort of middle of the way, and others, let's say, for instance, sodium atom that's got 3 energy levels.
You guys are cracking me up in the chat.
You'll have those that are close.
I hope he's almost finished.
to the nucleus.
But thanks again for the super
middle
chats,
of the way,
guys.
away from the nucleus will be another
I don't know what
bunch.
this has got to do with.
And then
I mean, this is specifically
further away will
about
be
thermodynamics and gas.
Oh,
but-
shit, you just woke me up, Flatzoid.
Now, these electrons are in discrete energy levels. Okay, so in other words, they have their place, they have where they belong, where they found most of the time. Not all the time, it's where they're found most of the time. So if we used Boltzmann's curve, you'd be able to track where, so 99% of the time, those electrons with that particular type of amount of energy will be found in this particular region of the atom. Now, what happens is when you heat something up, like for instance, if you've got a piece of metal and you stick it on the stove and it starts heating up and getting red hot. Okay, so what happens then is that those atoms, those electrons, are now moving from that energy state where they were when the thing was cold, and they're moving to higher energy states where they normally wouldn't be. Okay, that's because this atom is absorbing the energy. Now, what happens is they can't stay there. So they're always giving up that energy again. So they collect this energy from outside and then they give it up. And it's that process of giving it up. It's because they've got to get rid of this energy. How are they going to get rid of this energy? They give up this energy in terms of photons, in terms of light. Okay? So that's how that energy happens, and that's how we get electromagnetic radiation. So in a simplified way, all matter is made of atoms at any temperature above absolute zero.
Guys, I am on the generator at the
basically
moment. I
everything.
am in load shedding. It's coming on
These
in about
atoms are
25
moving
minutes.
and colliding with each other. The atoms contain positive and negative charges, as I said before, and the motion of the atoms and their collisions with other atoms affect the motion of the electrons. I think that's oversimplified. Okay, I would go with that, with the way I described it before. So in other words, you're heating it up as it goes back to its ground state, gives away photons.
Transfers. Yeah.
All right. Yeah. All right. So a hot object produces radiation across a broad range of wavelengths. Okay, so it's not just one wavelength. Okay. If its temperature increases, the atoms move faster and have more frequent and more energetic collisions. These produce more intense radiation with higher frequencies and shorter wavelengths. Okay, so shorter wavelengths means more energy. Okay, but still this occurs across a range of frequencies. So in other words, it's not just one color. So we look at a fire and you can see it's got different colors in it, and that's because there's different ranges of frequencies. Things are hotter than other things, or the heat required to move those electrons from one energy level to another is different in this particular one for that. That's why when you heat up, if you remember when you were in school, you did the flame test, and you could see that different elements produce different colors. Okay, for that reason. Okay, so how can we tell the temperature of the sun? All right, this bit's going to be controversial with flat earthers, but never mind. We're going to go through it. All right, so as the black body radiation model, remember I'll say that again, it's a black body radiation model, okay, proposes the sun emits photons at a frequency that is proportional to temperature. Just like everything, just like the hot iron, right? Put something in the stove, it's going to heat up to, it's going to be red. Leave it there, it'll be orange. Leave it there, it'll be white hot. Leave it there, it'll be blue, right? So it's going to change with
Every
temperature.
time I think he's done, he has something else to talk about.
Temperature is proportional to the colors that you see it is. So the range of frequencies and corresponding temperatures have been empirically measured millions of times by people such that an accurate range of temperatures can be determined by the frequencies. So it's empirical. You look at a different color and you can set that against a table of colors and heat, and you can say, right, that color is that hot. That color is that hot. The sun is this color, therefore it's this hot. That's how hot it is, right? There's a relation.
So you would say the sun is white then?
Yeah, well, the sun is pretty hot, so in other words, it's not quite white, but yeah, no, it's getting to, it's
almost white. You could
white.
say.
It's exactly. It's pretty hot. Okay. So now, can we measure the distance of the sun? Well, yeah, of course. Right. Remember what I said about black body? Well, there's no such thing as an absolute black body. There's a real one. Black body is a model. No such thing as a perfect black body object. So we can bounce. Electromagnetic photons at frequencies around 30 to 38 megacycles per second off the surface of the sun. So if we can do that and we can get them back, then we just need to know how measure the time that they take to get back, because we know the speed that they go there and back. Now I've heard people say, "Oh, how do we know the never measured the single light in a single direction? Doesn't matter." If it goes there and comes back, we divide it by 2. We got it. Okay, it's not a big deal. So the first, this is first immortalized in a paper by Ellemnet et al., which is, when we say et al. in papers in science, we mean and their friends, and that was in 1960, published in the journal Science. So, and there's numerous other trials using radar have yielded the same results. So, and all of them comport with the traditional parallax methods, as well as the calculated distance predicted by Kepler's laws. So, Kepler's laws tells us about the orbits of these things around each other. I mean, we can't argue that Venus goes around the sun. We can see it. We can see it happen. We can't argue that Mercury goes around the sun. It's within our sphere. We look at the planets and we go, oh, there it is now. Oh, there it is there. Oh, look, 6 months later, it's over there. Well, it went behind the sun. Well, yeah, okay. So all these things are empirical. We can see them. We can measure them. All right. And Kepler, what he did was really do all those observations. And by making those observations, then realize that, hang on, if you plot all of these things, you can see that this turns out to be an ellipse. And that's the orbit. So, numerous other trials using... Oh, I've said that before. Okay. All right, so, in the sun,
This is
extreme pressures... So the question is, what's the sun made out of? All right, that's another question that's asked a lot. Okay. So, in the sun, the extreme pressures produced by the immense gravity creates the conditions for fusion to happen. So this sun is a very, very big damn thing, right? And because it's so big and it's so huge, it's got a lot of gravity. Okay, and this is a lot of pressure. It's this amount of energy, the intensity of this energy, and the products given off, such as high energy electromagnetic radiation and neutrinos, provides the evidence for the power production of the sun. So it's not like we're saying, gee whiz, let's just have a guess at what this thing is. We don't have to guess. Okay, we know, we can predict what would happen if we did have a fusion reaction. We can then predict what would happen if we had a fusion reaction the size of the sun. Okay, and if we did have something the size of the sun, then we can predict what it would need to be. So we know it's hydrogen helium because we can see their specific absorption spectral lines. Spectral absorption lines are uniquely placed for each element. Remember, I explained to you before about the energy, reaching its absorbing heat, and then letting that heat go. It's the reason for why these black lines appear. Okay, right? So these black lines, they're very, very specific to a particular element, which is a handy thing for it to be. All right. So we can have a look at the spectral lines, at those absorption lines, or in fact the emission lines, which is sort of the opposite of this, right? So whereas you can see the black spaces in between here for absorption lines, for emission lines we actually see the colored. Those very, very same places are colored, whereas the rest of the background is black. Okay, right. So we know it's hydrogen and helium because we can see their specific lines, okay? And we can compare the spectral lines produced in the laboratory by hydrogen and helium. So we can have a look, this is what happened in the lab. We do the same thing. We have a look at the sun with a spectrometer and say, same thing. Well, every other element has their own signature, like fingerprint. Well, that one looks the same as that one. So, yeah. Definitely hydrogen and helium in the sun. Now, when you know that, and you know that there's a fusion reaction happening, then you know that hydrogen is the smallest atom, and then we've got helium. The hydrogen is therefore in a fusion reaction smashing those hydrogen atoms together and creating helium atoms. Okay.
So you're talking about spectroscopy here.
Yeah.
Yeah, I do spectroscopy at work. So.
Yeah, exactly right. Yep, no, you're quite right. Okay. All right, so can the sun be a hologram? Well, no. The sun is a physical object because it's a plasma, so plasmas have to be physical. They not only have to be physical, but they have to be really, really hot. So, okay? So we know it's a plasma because it needs to produce the energy that it does. Okay, and this isn't something that we can't see. This picture that you're looking at is the actual sun. Okay, this GIF comes from an actual a video, right? Well, video is not the word. Film. I don't know. I'm getting old, and the older you get, you lose words sometimes. Unfortunately. I don't know. I forget things that are very, very happened just 5 minutes ago.
I just got to say something. I'm not sure how long my petrol's still going to last in the generator because I only had half a tank. But the power is coming on in 15 minutes. So if it does go off, my petrol just ran out of the generator.
Yeah, no, it's okay. It's okay. We look. I'm happy to continue. At the time, so it's not a problem, right? If we have to, but I think it's important that we all have a good listen to a lecture, and whether or not you accept it or not, you've heard what the scientists out there are saying about it, and you got an accurate view of what they say and why they say it. And I think that's important. Okay.
Yeah.
Part where I said Professor Phil says this and then Flatzoid says this.
No, I just missed that.
Yeah, you didn't.
Yeah.
Okay.
Maybe
right.
start there.
All right. Well, I'll just go there if that's something.
Okay.
Not a problem. Okay, it's not a problem. We're nearly at the end of it, okay?
Okay. So
Okay, tell me when you're ready, okay?
Okay, you can go. It's fine. So he didn't
All
even
right,
know,
so
guys.
this summary. Okay, so obviously something is. So you can see my screen. You can see all of the different things. Yeah.
Yeah.
So obviously something is stopping the gas from rushing from the thin blue area to the vast black area we call space. Okay. All right. So we call that black area space. You can call it what you like, Narnia, Farnia, whatever. Doesn't matter. Right, we call it space. All right. And in that space, we do things like put satellites and the like. Okay. So flat Earth hangs on a single precarious thread of misconception about thermodynamics, particularly the second law of thermodynamics. Space below 100 kilometers accounts for about 99.997% of Earth's atmosphere. And the area between the ground and 30 kilometers accounts for about 99% of Earth's atmosphere. But this doesn't happen suddenly. The drop in pressure is exponentially less and less. Whatever reason flat earthers will assert why the air at the ground doesn't rush to fill that vast black area, the fact remains that it doesn't do it. Okay, so using your logic, it must be violating the second law of thermodynamics. Okay. All right. So though that black area, that meets the absolute very definition of space. Okay, so does space exist? Yeah, there it is. Look at it. Okay, it's that black stuff. That's space. What do we do in there? We put satellites in there. Why do we need to put satellites in that black area? That's because we don't need it can't have drag. Okay, if it has drag, it's going to fall back to the Earth. In order for a satellite to do what it does, it has to go extremely fast. Right? Let's go. If you've got things like air particles and that dragging it back, eventually it's not going to be fast enough to be able to keep orbiting. It's going to fall back to the Earth. That's why it's got to be in that black area that you see over there. All right, so let's talk about some empirical facts. So flat earthers. So first of all, the atmosphere gradient gets potentially less with altitude. That's an empirical fact. The atmospheric gradient gets exponentially colder with altitude. That's an empirical fact. And temperature is proportional to kinetic energy. That's an imperial fact. So let's go over a recent conversation between me and Keith over here. Okay, so. I'm not saying that's an actual conversation happening, but it would be a conversation that would happen if we did have one, all right? So, I would say, why does the air in the blue not rush to the vast black area? I've actually asked Keith that question, all right? And his answer was gas behavior. Okay. And I've said, but no matter what gas behavior you think is stopping the air from dispersing into the vast black area, the fact is the second law of thermodynamics is not doing what you and flat earthers say it must do. It's not moving that air from the ground up into that black area. It should be, if the second law of thermodynamics had anything to do with it. So obviously, something is stopping the gas from rushing to that vast black area. What is it? Well, the vast black area meets the definition of space. So why is the second law of thermodynamics not forcing the air to undergo entropy and force the air from that thin blue area on the ground to rush to fill the black area so that it can reach equilibrium as you'd expect it to, as you keep saying it will happen? As I pointed out to you in this lecture, that it happens in a container. If you have a container, that's what's going to happen. Okay, so yeah, you can saw that in that bromine thing. Okay, so what is it then? Oh well, clearly flat earthers can't rely on the second law of thermodynamics to make their case for why space has been fact. Space exists. We can see it. The area above the thin blue area is black. because there's not enough particles to scatter blue wavelengths of light. Now, I actually asked Keith this question. I asked him, and I was fully expecting the right answer, and I got the right answer. And Keith said that because light passing through the air particles scatters the blue wavelengths. That's why the sky is blue. Absolutely correct. All right. So the fewness of of air particles, fewness, I looked it up. It's actually a word, right? In the vast black area, is corroborated by empirical measurements of gas particle concentration and pressure. We're not wondering what's there, that it's hardly got any. We know, right? We can measure it. We do not see a container stopping the air in the blue area from rushing to the black. There's no container in between, so still not doing it. So where most of the space, and we've got all this activity happening in that space up there, no container in between it, because we get from the ground up there, so nothing's stopping us from getting. There's no container there, right? Where is this container? I don't expect any flat earthers to change their mind, all right? And I expect them to push back, no doubt about it. You'll have a lot of fun with content going through this, I'm sure. Okay, the second law of thermodynamics assertion is a very big deal for flat earth, for the flat earth hypothesis, okay? In fact, the flat earth hypothesis is perched on the most slender of threads, okay? The most important being the hope that the second law of thermodynamics is sufficient to deny that space exists. However, as I clearly demonstrated in this lecture, this slender thread is broken by the misunderstandings of what constitutes thermodynamics, and particularly what the second law of thermodynamics is about. And it's smashed by the visual evidence of the vast black area above the 99% of the atmosphere in that thin blue area, without a containment in between. Flat earthers may continue to assert that Earth is flat and space is flat. Go for it, It's fun if you do. I'm not saying stop doing what you're doing. Okay, however, if they're genuinely interested in truth, hopefully this lecture will prompt them to assess their position and search for a new hypothesis that explains why the gas isn't rushing off to fill that okay, and why they think space is fake. You need a new hypothesis. Forget the second law of thermodynamics. Doesn't work. Okay, so no doubt the flat earth influences like Quantum Razor and Oakley and maybe even Keith, right, will continue to cherry pick articles or sentences that describe entropy as the gas they're trying to, and they'll use that to try and deflect. But entropy has long been co-opted as a synonym for dispersion. So when they call something dispersion, they call it entropy, right? But that's not physics, okay? Physics has a particular definition for entropy, right? It's important to add context to the word. That's because words in physics are precise and important. Entropy is, in the context of the second law of thermodynamics, is much more than dispersion. It also requires caveats like energy, irreversibility, and unidirectionality. All right. For the most part, gas dispersions can always be collected, right? And process can be reversed, all right, given the right conditions, right? So even gas dispersing from the nozzle of a rocket would not satisfy the process of entropy as described by the second law of thermodynamics, because those gases will form part of the gas cycle on Earth. They'll be collected. They'll be used again. The process is reversible. Oxygen and hydrogen will become water. It's reversible. The heat energy, though, that's not reversible. The heat energy during the combustion reaction is the entropy in the context of the second law of thermodynamics. You've got to be specific, okay? Because there is no way to collect the heat and make it do work. That's imperative for entropy. The entropy of that heat energy continues to increase in the universe. So, describing the dispersion of matter in terms of the second law of thermodynamics without the context of energy is a red herring. It's not by magic that the air in the thin blue area, where the pressure and concentration of air particles is higher, that these particles are not subjected to the second law of thermodynamics, and therefore forced to equilibrate by rushing to fill the vast black area where the pressure is reasonably described as a significant vacuum. In other words, space. To that end, it's incumbent on flat earthers to develop a hypothesis to explain why the air in the ground doesn't rush to fill that vast black area. It's obviously, it cannot be violated by the second law of thermodynamics. Well, you've got to ask, well, why is it then? What do the other people think? Well, let's think back to the deep mine that's filled with CO2, right? South Africa's full of mines, deep, very, very, very deep shafts. Right, it's a big mining country, just like Australia. So this is generally referred to as a confined space, right? So why does CO2 stay at the bottom of this mine shaft? Okay, why are we able to pour CO2 into a liquid? All right, you get a cup of CO2, you can pour it. It goes down when you pour it. Why is the concentration of CO2 greater as you approach the bottom of the shaft? And can you think of ways to solve the problem of CO2 accumulating at the bottom of the shaft? These are questions that you can answer. And if you answer A and B as gravity, congratulations. Unicorn farts, good on you. You said RDD? Okay. Not because RDD is the right answer, but because it points to the fact that you recognize the fact that gases do go down if other forces are unable to overcome the force downwards. So congratulations, RDD people. If your answer was C, temperature and kinetic energy plus the weight of the atmosphere, that is the reason for the pressure down there. In other words, it's the weight of CO2 plus the weight of the atmosphere above it. That's what the pressure is. And if you bought that, take a bow. And if your answer's for what can you do about it, and you said put a ventilation shaft in, add some air, brilliant. That's because you're adding energy to the system. You're forcing that translational kinetic energy to happen to that CO2. It's going to move around. Air is going to take its place, and with all this movement, you've got to keep that ventilation going. People will be able to breathe down there. Okay, so if you said all of that, you're a genius.
Okay, so are you finished now?
Almost. You have a couple of minutes. Right? Air particles have different amounts of translational kinetic energy, as I said before. Okay, all right. So, why do we have a pressure gradient? This is the last thing, right? Okay, we have a pressure gradient because particles have different translational energy. They're going to get, some are going to get so far, others are going to get further, others are going to get further again, but eventually all of them, or most of them, 99.997 of them, are going to be stopped. I don't mean stopped as in 0 Kelvin. I don't mean that. Okay, I mean that they're going to not be able to go any higher. They're going to get so high, they'll come down a bit, they'll gather some more energy, they'll go back up again, so they'll be hanging around that sort of level, right? So, and this happens throughout the thing, so that we end up with a gradient, right? And this gradient's always constant. We see the same thin blue area above the black area every time we launch a balloon. Okay, so a container is unnecessary to keep 99% of the atmosphere in the blue area. So what's pressure? Remember what I said to you before about that? Pressure is the weight of the atmosphere. Okay, the weight is the force pushing down as a result of the product of mass and gravitational acceleration. Pressure is the amount of force or weight on a unit measure of area. Right. I'm going to try and skip a bit. Right. So my final words on this. So the second law of thermodynamics is a red herring, designed to trick people to thinking that space is fake. Okay. And that a container is necessary. It should now be obvious to everyone who listens to this lecture that space is fake, that the assertion that space is fake is unsupported by evidence. Thank you for participating. Okay.
Awesome. Thank you.
All right. I'm just going to let me get to. Oh, I went too far. There you go. That's my last slide. Okay.
Cool.
Okay. Can you stop me sharing, or will I have to do that?
Yeah, I'll do it like that. There we go.
Okay. Good on you. Well, that was something. There you go.
So I've got a few rebuttals though.
Oh, well, I bet you have. Look, it's 7:26. Let me take a few questions because I am running out of time. Okay, I wasn't expecting to take this long. But, there you go. I think we've got a bit out of this. At least.
Unless you want to come back for just a chat about
of course
this, then.
No problems.
Then we can do an actual, because I got quite a few things to say about the information you brought.
Sure.
Because it is quite late as well at the moment. And I do appreciate you coming so early. I know it was 5 a.m. by you when you started, so...
How can you make
that's right. Yeah, exactly. Yeah. And plus, I'm not well, you know.
Yeah.
So that didn't help the situation. I've got a really sore throat.
Yeah.
But you know what it's like. I one thing I have to... You seem to get a lot of headaches, all right? And,
I used to.
And yeah, you need to check that out, Keith, I reckon. You know, I'd hate to see something happen to you, all right? So get it checked out, you know, because you never know, there might be something lingering there.
It's just something that runs in our family, though.
Yeah, no, I know. The same thing happens to mine. You know, my dad used to get migraines a lot, and, you know, some of my brothers do, and I certainly have got that, and my daughter's in that same bag. It does run in families, but you never know. Sometimes there's something innocuous that you need to deal with. All right.
Yeah.
Anyway, thank you very much, Keith. You've been very graceful. I appreciate that very much. Okay.
Cool. Thank you very much for
coming.
And
I'll be back so that we can go through this, and then you can ask some good questions.
Then I'll give my presentation based on your information you presented. How's that?
Totally.
Okay, cool.
Okay. I wouldn't think I would think no less. Okay.
Awesome. Thank you very much. Really appreciate you
coming. Good on you, mate. No worries. Okay. All right. You kick me out. I have a clue how to get out.
Okay. You have a good day further, mate. Cheers.
You too. Take care.
Okay. Well, we don't need to get you guys to Ellemnet then. To StreamYard.
Yeah. I've been debating on going to bed for the last 40 minutes.
So yeah, what I'll do is I'll take the information you presented, and then I'll do a presentation on it to rebut him. But I got 2 words that debunks his whole argument. Wait, let me just quickly bring it up for you guys.
What was it? Elastic collision.
Let me see if I can bring it to screen for everybody.
Elastic collision. I was right. Elastic collisions.
Can't say that.
Elastic collisions.
Just those words alone debunk his whole argument.
Yep, that's it.
I had a question. You know, when you were talking about bromine next to vacuum and that, and he said that like there's an heat loss through glass, but when that guy does that demonstration,
I'm going to show you now the video. I'm going to show you the video now.
He says there's no heat loss or anything. There's just entropy. That's all it is.
That's the thing. What he's trying to do, he's trying to ignore Joule's free expansion of gases, and even his irreversible argument is false. I just gotta quickly say, I gotta say thank you for the super chats, guys. If I haven't read super chats out already, I'm sorry. I'm gonna quickly read them out now, but then I'll show that video.
There is a few, yeah.
Retro Ball, thank you very much for your $10 super chat. If Big Bang, all matter would expand outwards from the center, leaving behind a giant void, aka matter expanding into one void while leaving behind another. Thank you very much for the super chat. Yeah, the thing about the Big Bang, it does violate the first law of thermodynamics because they had to have the energy present from nothing. Nature can't create itself. You would require supernatural intervene to have their dense speck of infinite substance there to be able to expand. You understand? So that's why it does violate the first law of thermodynamics, because nothing created itself to expand. So yeah, he's already going to step 2 from the expansion and saying, oh, but the expansion's not violating the first law. No, the expansion doesn't. It's the fact that it has created itself to expand that violates the first law. Lumpy Gas, thank you very much for your $2 super chat. Full, can gas spontaneously lump in a vacuum? Nope, definitely not. Thank you very much for the super chat. Then Face Reality, thank you for your $5 super chat. A pity all the students in Phil's classroom eagerly waiting for the bell to ring. I did feel kind of long-winded by a while. Yeah, it was a very long presentation, and it was only supposed to be about thermodynamics, so he tried to go through everything of thermodynamics that I think was really unnecessary, actually, but it's fine. I let him say his say, and I didn't, interrupt him or anything. So
can't knock him for getting up early, is ill, and he's going to presentate. You can't knock him for that, right? But it was long-winded.
At least he eventually give it a go, I mean, we've been trying for ages to get him in. He's coming. Yeah, I mean, it was long-winded and that, but I'm glad he did. You know what I mean? Because it lets us see where he's at. And like you said, those 2 words alone debunks his whole.
Yeah.
His whole.
And I really do would appreciate if he does come in for that chat, like he says, because because I can also do a presentation that goes and shows why his assertions are wrong. The thing is, the information he gave is correct based on the thermodynamics and stuff, but there's a few nuances he's missed, very critical things that I don't know if he intentionally omitted them, kept them out, and he added a few things, you know what I mean? So, but yeah, I'll be doing presentation on that then. But let's quickly look at the video.
One of these bulbs, some bromine, and in the other I have a vacuum. And if I open the tap between these two, you will see spontaneously the bromine rush from one to the other. Now that is the simplest change we can have, perhaps, because all that happens is a change in entropy.
Listen here, guys.
In this case, the expansion into a vacuum, nothing else is involved. There's no energy change, there's no temperature change, there's no change except entropy.
You heard that? No energy change, no temperature change, only change in entropy. Now, the thing that Phil Bell was talking about was the bromine will have an reversible process, so then it will turn to liquid form. Ignoring that all the bromine was in that one volume, set volume. Now that it has exchanged and gone to a larger volume, it's got larger volume to contain, so the bromine has separated, correct? So that means when it becomes liquid, you'll have a little bromine there and a little bromine there, where all of it was in the same volume before. So therefore entropy has increased, and it is not a reversible process, which he ignored. But yeah, that's very simple. That's the one you wanted me to show, Michael, correct?
Yeah.
But yeah, I'm definitely going to do the video, as I said. But anyway, guys, I really got to go. I didn't think he was going to go this long on.
I know, yeah.
I've been telling my idea going to bed ages.
It's crazy. So any closing statements? Sorry we didn't speak much. We could have just had a live stream titled Full Bell Talks.
That's it. Let me say my closing statement is just what you said. I seen you put it up on the screen earlier on. Elastic collision.
I wish you'd have just presented thermodynamics without all flat earth stuff involved with it. I mean, it said thermodynamics is bad for flat earthers, but like flat earthers, what does that mean? Like, it means that the ground we dwell upon is flat.
Yeah.
I mean, I didn't appreciate the minions thing and all that, and flat Earth is a conspiracy theory, you say, and it's not. It's observable and demonstrable. You know what I mean? So how is it a conspiracy theory?
It's not an hypothesis, and there's no model either. Like.
Exactly.
Okay.
There you go.
So I'll see you guys all tomorrow night then. No, Wednesday. Sorry, tomorrow night's Michael's show. You going to have a show tomorrow night, Michael?
Yeah, tomorrow. I apologize for last week, but life's life, innit?
Awesome.
Yeah.
Yeah, guys, there's no Ball Busters tomorrow night. QE let know he's on Thursday. So everybody can make it to Michael's show tomorrow. Yay.
Exactly. So we'll be expecting no less than 1,000 viewers. Fast chat and everything.
And if possible, come on the stream.
Yeah, definitely.
Come on. We need more people on the panel.
So cheers. So guys, I should say thank you for coming. Really appreciate all the support. Please hit the likes if you haven't. Share the show. Thank you for all the super chats. Thank you for all the support. Sorry that we had to listen through all that. I really didn't think it was going to go on that long. But yeah, I'll see you guys all then Wednesday, and have an awesome evening or day further. Many, many blessings. Cheers.